Welcome to all of you. Myself, Dr. Aravind B. I'm going to present on the topic Image Denoising Basics and Futures. This is the outline of the presentation. Introduction involves why denoising is required. Then literature review. It involves the details related to the both spatial as well as the transform domain denoising. Then one method is discussed with respect to the spatial domain denoising process incomplete. Similarly, one more process is discussed with respect to transform domain image denoising concept. Then an additional method with multi-level image denoising is presented. Then at the end we are going to have the conclusion and the future scope of research in the image denoising. Coming to the introduction. So basic definition of the noise. Noise is an undesirable part of the signal. Okay, so denoising is always considered as a pre-processing part in any of the image processing techniques. For example, here a concept of segmentation is presented. A original image without noise has been taken. After segmentation, this is the result what we have got. This is the desired result. Noise has been added, and then for the same image the segmentation is performed, and here lot of information has been lost, and that we can identify by comparison itself. So that means if in the pre-processing, if you are not going to perform the concepts like image denoising, it is going to create a problem in the further image processing techniques, and it may be segmentation, enhancement, reconstruction, or whatever it is. So it is going to create a problem. Therefore image denoising is a must and should process. Few more images are being presented over here. A satellite image, so where we can observe this region, almost all the image is heavily noised. So this complete region plus this part of the region as well as this part of the region, that belongs to a town region, and this is just like a river representation, and here we are not able to identify any kind of buildings, roads, trees, or whatever it is. Distinguishing is not at all possible. Effect of noise. Similarly, one more is presented with respect to the CC camera image taken during the light time, a low light imaging, and it is difficult for us to identify either a person is standing over here or it is something like a signboard or whatever it is. It is not possible to identify. So the person is also not much clearly visible. If his face is towards the camera, still his face may not be recognizable manner. So that is due to this large amount of noise what we are going to have. Now coming to the degradation model. Degradation as well as the restoration representation we are going to have. So this is what the degradation and the restoration model we are going to have. X is the original image. It is going to be degraded with the degradation function h. Then the noise eta will be added to it to generate the degraded representation y, and this y has to be restored so that we can get back this x once again. Therefore this y is passed through the restoration filters to obtain the restored image x cap. Remember, we always represent this restored representation by x cap only, not by the x, because this x cap can never be 100% same as that of the x. Therefore we call that as close to x. That's why it is x cap. In the mathematical format, it is represented by y is equal to, y is the degraded representation, y is the x is equal to x convolved with h plus the noise component. So we are not going to, in the further discussion, we are not going to consider this degradation function h. Our discussion is limited only with respect to the noise. Therefore this formula will take the form y is equal to x plus eta. Remember, we are going to make use of the term plus. Therefore the type of the noise we are going to consider will be usually additive type of representation. Now coming to the various noise models and also the way they are going to obtain. So based on the probability density function, we are going to define these many types of noise. So Gaussian noise, and it is due to the poor illumination. Rayleigh noise, we are going to obtain that in the modeling range imaging. Erlang or the gamma noise, in the laser imaging, exponential noise in the laser imaging, uniform noise due to the quantization of the intensity levels, impulse noise, black and white spots on the image are called the impulse noise. So of the so many types of noise, our consideration is only an image corrupted by the Gaussian noise. So all further discussion we are going to have, either the literature survey or the methodologies being said, so they all belongs to the removal of the Gaussian noise. And also we are going to consider only the generic images, that means test images we are going to consider. We are not in particular with any satellite image, medical image, or any other types of images. We are just going to take the test images and we are going to work out on that only. Now coming to the literature review. The literature review is broadly categorized into two parts: literatures related to the spatial domain methods and literatures related to the transform domain methods. So let us take one after the another. First, the spatial domain methods. In the spatial domain denoising, it involves pixel by pixel manipulation, the direct pixel value manipulation. So it is going to consider this local neighborhood pixels. Therefore, the local mean and the variance are going to play an important role. Now, there is also a sentence being said in the literature: image denoising is a well-studied concept. What's the meaning of well-studied? So, concept of noise and the denoising is in existence from long back. So that's why 1976 we are going to take the literature. So that means it's a well-studied problem. So Wallace defined local mean and the variance, then Lee extended this by making use of a constant value. So I'm not going through this mathematics, you can just go through. There is several mathematical parts we are going to have. You can. And then Tomasi and Manducci introduced the bilateral filter. Rudin and Osher introduced the total variation minimization for continuous signals. Its discretized version was developed by Chen et al. Then Jin et al. Proposed an adaptive approach. Then Budes et al. Introduced the concept of non-local means. This further literature review involves the improvisation of the already introduced methods like non-local means. So it was introduced by Budes et al., which was taken further 2011 up to 2018. Then methods like single value decomposition based methods for image denoising were introduced, and so some discussions were taken further also, and one paper of 2016 is being said over here. Then BM3D, another method. Then 2015 its improvisation still happening, and it is in 2018, and one more BM3D method in 2019 has happened. So here we have to observe that the major changes were happened in the year 2000 to 2010. So later on the methods discussed were most of them were the improvised version of the existing method. Some additions, some changes has been done, and they were keep improving even till today also. And there were several methods like Monte Carlo Markov chain techniques, then map MRF approach, and then principal component analysis, independent component analysis. So using these concepts also several image denoising were proposed. So in the further discussion, what I told in the spatial domain, I am going to explain you one method. So that is based on this Markov random field approach. Now coming to the literature review related to the transform domain denoising. So purpose of image transform is to cluster the image based on its frequency distribution. So that is what the major concept. Based on that only we are going to work out with respect to the noise. So that means usually noise will have a higher frequency component and signal is comparatively low frequency component. So when a transform is applied, it is going to separate out this noise and the signal. So once we got it separated, then removal of the noise will become quite easy. So that's what this is helpful in separating signal and the noise component. So once they are separated, then we are going to apply a simple but effective rule called the shrinkage. Right? So shrinkage is nothing but we are going to identify a threshold value, apply that threshold value on the coefficients, transformed coefficients. So we are going to get the results. We'll have a detailed discussion later. In this particular literature review, we are just going to consider the wavelet transform. Therefore, so first it is better to define why we are going to take the wavelets. So these wavelet transforms are able to separate the fine details in the signal. With respect to one dimension, I'm going to have an example somewhere further. There we can clearly understand that. Then time frequency localization it is going to have, that's the major property of the wavelet. Then decomposition is mathematically reversible. This is the most important part. Now coming to the details of the literature review. A pioneering work in the wavelet based denoising was proposed by Donoho. He proposed soft and hard thresholding. So the soft thresholding is defined as it is kill or shrink process. What it means for? So kill process. So we are going to have a threshold value. Modulus of the wavelet coefficient is compared with that thresholding. If it is less than or equal to threshold, so make that coefficient equal to 0. If modulus of that wavelet transform, a wavelet coefficient is greater than the threshold, then shrink it by the value of the threshold. That's why kill or shrink process. Hard thresholding is kill or keep process. If it is less than or equal to threshold, make it equal to 0, same as the previous. If the value of the wavelet coefficient is greater than that of the threshold, then keep it as it is. So kill or keep process. So these are the major strengths with respect to the thresholding technique that is going to drive many of the wavelet based techniques. Then this techniques was extended to translation invariant method, where several shifted versions of the noisy images are being used. On each of them the either soft or the hard thresholding is used, then they are reverted back and then averaged to obtain the denoised representation. This is what the formula for that. This gave better results compared to the direct application of the hard or the soft thresholding. Then this method was extended, that is translation invariant method was extended to translation invariant multi-wavelet transform. Multi-wavelet transform was used along with this translation invariant concept to obtain better results. Then firm shrinkage was introduced, which was also called the semi-soft. In the previous slide what we had gone through, that clearly says one threshold value is being used. Here they have extended that work to and made use of two threshold values, T1 and T2. So in the complete shrinkage process we are going to have two important concepts. First one, identify the proper threshold value, and also identify the way it is being applied on the transform coefficients. So based on this only the quality of the result completely depends. Therefore, so here they define two threshold values. So here we can observe the kill, keep, shrinkage. All these three concepts are being involved over here by making use of the two different threshold values. Therefore, this may give better result when compared to the previous one. So like this, several other thresholding techniques and the way of being applied are defined by these three different papers. Now, what all we discussed in this slide, so with respect to literature as well as in the previous slide, they are going to make use of the term by term application of the thresholding process. That means take a coefficient, apply thresholding, then keep it back. Take a coefficient, apply thresholding, keep it back. So they are not going to consider the effective effect of the neighborhood wavelet coefficients on one center pixel. It was identified in the later literature that in the wavelet transform the surrounding coefficients will have an effect on the center coefficient. So there were several methods proposed based on that also. So the major ideology there was large wavelet coefficients have large valued coefficients at its neighborhoods. So based on this concept, the neighborhoods were considered, and then several papers came out of it. All these methods makes use of the neighborhoods. So niblock and the Markov applied on 1D extended the same to the multi-wavelets, again 1D, and both of these two are applicable to 2D also. Then translation invariant nice string was proposed, the nice string sure was proposed. So these are all based on considering the neighborhood coefficients in the wavelet transform. There's one more method called the bivariate shrinkage, so separately mentioned. This makes use of the parent-child relationship. It says that if a parent is going to have the noise component, then obviously the child is going to have the noise component. So this will work with respect to the wavelet decomposition. So that's why this bivariate shrinkage is a different concept in the wavelet based denoising. Now there were several papers related to this concept, artifact-free wavelet denoising, and then image denoising with morphology with the block matching transform. And then one special paper that we need to consider here is a review of denoising medical images using machine learning approaches. So as I told you before, I'm not going to consider anything specific with respect to medical or the satellite images, but one paper I must mention over here that is related to medical images, because for denoising purpose this is clearly going to make use of the machine learning approaches. Since this is a review paper, obviously there is all the possibility that we can get most of the information related to the way machine learning is adopted for denoising purpose. There were several other transforms which I must mention that can work with respect to the denoising. So that involves the complex wavelets, contourlets, wedgelets, surelets, and also the discrete cosine transform. So contourlets, I will just take this one for example sake. Contourlets were developed in order to capture the smooth edges in an image, which was quite a difficult concept with respect to the wavelets. Therefore, as an extension of the wavelet, the contourlets were developed, and for particular cases, this worked very well with respect to denoising also. So, the interested persons can just explore these concepts in detail. Now, coming to the issues and the challenges. First, the issues. The denoising always create the artifacts, the most problematic concept, and then the smoothing of the edges. So if you want to suppress the noise to a better extent, that also smoothen the edges. So that's what the concept, the issues we are going to have. Challenges: remove the noise. So that's what the basic concept we are going to have. Preserve the edges, must not get smoothened. So both of these achieving together is a quite difficult issue. Therefore, we are going for a trade-off. So trade-off between noise removal and preserving the edges. So we are going to address this when we go through several results with respect to the image denoising. Okay, so coming to this further discussion. So in this part of the discussion, I'm going to explain one method that is related to the spatial domain, and one method related to the transform domain, and there is one more method that is multi-level denoising. So why I'm taking all of you through this process is, while making the research, it is always said, if you are going to have good mathematical representation as well as the realization, then it is much appreciated. So in order to have a better understanding how we can design that from the existing or known concepts, I'm just trying to take you through a tour of all those things over here. So in the spatial domain denoising, I'm going to present a discontinuity adaptive MRF technique that will perform the denoising and also preserve the edges. In the transform domain, I'm introducing this multi-spinning concept, and also an extension of that we are going to have multi-level denoising. So two different levels, at two different levels the denoising is performed. So let us take one after the other. First one we are going to have in the spatial domain method. Okay, so in the spatial domain denoising, image denoising is a ill-posed problem. So here we have to identify two terminologies. One is the ill-posed problem and one more is well-posed problem. Remember, ill-posed problem and the well-posed problem. let us understand what is this well posed problem. So in case of well posed problem, we know everything. That means what is the original image, what is the type of the degradation happened, how it has happened, and what is the existing content we are going to have. That is well posed. Each and every stage details we are aware of it, or at least a certain amount of correct information we are going to have about that image, so that we can perform the reverse operation of it. Right? That's a well posed concept. Ill posed concept is going to say we are going to have the degraded representation, but we don't know anything about how it has got degraded and from where this degradation has occurred. So this diagram is going to realize this ill posed problem. So how it is being done? Y is the degraded realization or the degraded representation, and how we can get this Y? There are several possibilities. For example, from x0 after degradation it will lead to Y, x1 after degradation it will lead to Y, like that n numbers, xn after degradation it may also lead to Y. So that means there are around n plus 1 possibilities from which we can get this Y. Now our problem is we are having Y, that's the degraded version, noisy image we can consider. So we are having this Y degraded version. I don't know from where it came from. That means I don't know about anything about this degradation or the original source, nothing, I don't know. But I want to reconstruct this once again back. Right? For example, for better understanding, if we consider the value 4, make an assumption 4 is the degraded version. How we can get this 4? We can obtain it by 2 square, that is equal to 4, minus 2 square, that is also equal to 4, 2 plus 2 is also 4, 3 plus 1, that is also equal to 4. So these are several possibilities out of which we can get that 4, but which is the actual base of that value, we don't know about that. From either it is 2 square or minus 2 square, how we have got, we don't know about that. But still we need to reconstruct the original data. So here I am going to make an assumption that so Y is the degraded version and the x0 is what the actual data, and after degradation we got Y, and these are all some other disturbances or the possibilities which can lead us to wrong results. So because of which, just for the sake of understanding, I just represented this Y actually obtained from x0, and our requirement with respect to denoising is Y is given. I don't know any details about it, just Y is given, and I must reconstruct back the x0. Right? What it requires, let us go through that. Okay, now coming to the map estimation. So x cap is equal to argument maximizing the x, probability of x given Y, we need to maximize the possibility of x. And now to make ill posed problem as well posed problem, that is what is our requirement. It is necessary to know something about the image. That something we call it as the prior knowledge, right? So ill posed problem is given, and to make a solution for that ill posed problem, we must convert that into the well posed problem. How to convert? We must have certain information about that. So what is that information? So that information we are calling that as the prior knowledge. We are calling that as the prior knowledge. Now how to obtain this prior knowledge? As it is being told, nothing is available. Ill posed problem is nothing is available. But still we are saying, okay, we are going to identify something that is called the prior knowledge. Now what is this prior knowledge? Let us go through that. Now here we are going to have an image representation, a traffic signal image representation. So here we can make observation of few things. See, this complete area is of same color. Like that we can identify this area, and we can identify few area like this, and several such areas we can identify throughout the image. What it mean for? So in most of the region, these images possess constant gray level areas, right? So in very clear words we can say natural images are locally smooth, right? So that means pixels close to each other tend to have similar values. So that means a part of this image has been projected over here and its gray level values are presented here. Here we can observe that if we take this 3 cross 3 matrix, so all these pixel values lies in the same range. For example, not more than value 10 variation we are going to have. Within that range it is going to fall. Even though if I make this 107 is there, if I make this as 105, still we are not going to make we are not going to get any change with respect to texture in the image, because they are again close to each other, right? Whenever there is a change, so that is what the variation in the gray level value we are going to have. Otherwise this common area is going to have almost similar pixel values close to each other. In such a cases we can make use of Markov random field. So this modeling utilizes this concept. A modeling that makes use of this concept is the Markov random field, and this is the concept we are going to discuss further for denoising purpose. And remember once again, so we were there with the ill-posed problem. We require to have some prior knowledge to convert that ill-posed to well-posed problem, and that is available in the image itself. That is the local smooth concept, and that locally smooth concept is what the prior knowledge we are going to consider, right? Now coming to the Markov random field concept. So I'm not going to have very depth about this concept, just one statement and these two properties I'm going to mention, then we are going to have direct implementation part. A random field F is a Markov random field with respect to neighborhood system N if and only if it satisfies these two properties: positivity, Markovianity. Three different types of MRF models: Gaussian, Huber, and the line fields. So Gaussian always smooth in nature, Huber threshold minus t plus t we are going to consider, line fields so plus or minus square root of beta it is going to have, beyond which it is going to have so constant, no variation. Now coming to the problem formulation. So in the problem formulation it is quite important, so just go through these concepts. Let us go through these concepts. So observation model, so we are going to consider only the noise component, that is additive noise specifically. Therefore what is the representation we are going to have? Degraded version y is equal to original image plus the noise component we are going to have. Now the map estimation for this is given by x cap is equal to argument maximizing the x probability of x given y. Base rule we are going to apply. This is what we are going to get. This p of y is a constant value, therefore that can be eliminated, and equivalently this can be written something like this. So we need to convert this product term of this probability into the additive term. So therefore we are applying the logarithm on this one. So after applying the log we have got this one. Then now getting into the MRF Gibbs equivalence. So it is given by p of x is equal to x 1 by z exponential of minus u of x. This u of x is a energy component which can be written by making use of the click potential concept. Therefore now this is what it has been written. So now this p of x is now substituted over here, p of x, and now this expression now becomes something like this, right? So now we have to make one more substitution for this one. For that we are going to have the next. Now the noise fields are statistically independent of x and as well as each other. Therefore we are going to have this Gaussian component. So p of y is equal to y given x is equal to x. We are going to have this representation. Now substituting this in the previous equation we are going to have, and making the solution we are going to get this one. That means x cap is the reconstructed image, argument minimizing the x. So we need to identify the minus sign is there. In order to remove this minus sign we converted from maximization to the minimization. Y minus x square then divided by 2 sigma square, the noise variance we are going to have, plus the click potential value. So as a part of solution, three methods are being represented here. So all of them are based on the discontinuity adaptive MRF model given as DA-MRF. So DA1, DA2, DA3. So they are going to vary in terms of their representation that you can observe via the graph as well as through the equation itself. So graduated non-convexity algorithm is used for optimization purpose. It is going to start from the higher value of the gamma and going to decrement in order to identify the global minima. Now this is a simple flowchart realization. So start initialize the constants, update image and the count value, and remember this is completely an iterative process what we are going to have. So local minima, global minima concepts will be there. We need to identify only the global minima, therefore an iterative process is going to be work over here. So n+1 image is being identified by making the changes to nth image representation, and then count value is being represented. Then we are going to calculate the difference between the nth image and n-1th image. If the difference is less than the expected minimum error, then the process is completed, that x of n xn itself is the final image we are going to have. Otherwise, keep updating the constant, keep updating these values and keep iterating until we reaches to this minimum error value. Now these are all the some of the result part. We are going to have three images are being considered, the Lena image, then the child image as well as the boat image, because of their own specific characteristics. Now here is the noisy representation that we considered. Noise is going to have 10, so minimum noise we considered. Then few methods are being included over here, the bilateral filter, then non-local means. So here we can make the comparison. So bilateral filter feels to be over smoothed representation comparatively, whereas non-local means gives us the better results when compared to this bilateral filter. Continuing with the MRF method, so Gaussian MRF, it has clearly told it's going to perform the smoothing operation. So this is what we have got, and then DA1, DA2, DA3 we are going to have. Okay, so in order to identify to what extent we have got the results, a difference image with that of the original image has been taken. That means result we obtained, and with that of the original image we have taken a difference, and that difference has been plotted over here. So now I see leave it. Then bilateral filter, maximum amount of edges we are going to get in the in these images. It indicates that losses has happened to the larger extent. So bilateral filter, so maximum we are observing, so maximum loss has been happened. Non-local means minimum, like that Gaussian MRF and other three methods we can observe. Then a tabulation, it is just going to provide the results related to what we have gone through the various methods in terms of PSNR. In the three representations, that is Lena, child as well as the boat, we can observe that in the Lena and the boat, non-local means plays a very important role in almost this bold representation. That's what the highest PSNR value we have obtained, so that's what is the representation. And in the child image, which is going to have a specific characteristic of one part constant gray level area, another part too many edges with the text we are going to have, there this DA3 has given the better results over here. The qualitative analysis we are going to say for this, so that is the structural similarity index, mean structural similarity index, MSSIM we are going to have. So that is also being identified in order to make a finalization of which one is correct, because it is always said that in terms of PSNR, if you are going to get the highest value, it doesn't mean that structurally it is going to be exactly the equivalent representation. That's not possible. Therefore there is one more method we are going to make use to identify the quality of the image, that is the structural similarity index. You know, this is a quantitative value, but it is being considered under the quality index. So in the Lena image, non-local means gave the better results. In the child image, so one has to consider in case of the PSNR, here DA3 gave the best results, whereas in this one non-local means is giving the best results. Now in case of boat image, non-local means was the best with respect to PSNR, but here we are going to have DA3 is going to be the better one. So identifying these cases also works out in terms of denoising. Now coming to the noise estimation. See, what we considered previously was regular test image, then we added certain amount of noise, and then we only performed the denoising, so we have got the result. If we come to the natural images, then we don't have any idea about how much noise is present. So in order to identify that noise, in this particular presentation, I'm just going to make use of this median absolute deviation. Anyhow, nowadays there are several other methods available, but this is the most simplest method, and accuracy also given better for me. So that's why I just stick to this method. So this is what the formula for that one, and these are the three test images that I had taken for the estimation process: square, Barbara, and the house image. For the square image, the dark line indicates the actual noise component added, and this gray color indicates the value obtained out of this median absolute deviation. So here we can observe that 10, 9.8 I have got 20, 19.7 I have got 30, 29.5, so almost all are close. Like this, it obtained good for Barbara and the house images. Therefore I just stick to this particular case for the estimation of the noise. Now these are the real images that were taken. 1 second traffic signal image we have taken, and then just DA1, DA2, DA3, three methods are implemented. In a complete image, it is difficult to identify anything. Therefore this particular region was taken out and elaborated, and here is the representation we are going to have, and here we can identify the presence of the noise, right? And then DA1 denoised, DA2 and the DA3 denoising we can observe. So noise component is removed, as well as the letters edges are being properly maintained. So in the up to the previous slide, we have just gone through the concepts of spatial domain methods in detail. Markov random field, that is one method in detail. Now let us go through the wavelet based method for image denoising. So this is just introductory slide. I'm not going to have provide any introduction, just to wavelet formula, forward and the inverse we are going to have. So actual requirement is there in the next slide. Let us move on to that one. Okay, so in this we can clearly understand how this transform based method, or in particular the discrete wavelet transform, is going to work for us in the denoising with respect to shrinkage rule, right? Okay, now consider clean signal. So this one-dimensional data we have I have just considered for the sake of understanding. A clean signal, it has been taken. Apply the wavelet transform for this. So one stage wavelet transform we are going to get like this, right? Now same signal, noise is added. For that, wavelet is applied. So one stage again. So this is for the representation we are going to get, right? Now make a comparison of these two concepts: clean one stage wavelet, noisy one stage wavelet realization. What we can identify here is, so this is the high frequency component, this is the low frequency component. So in the high frequency component, there is no such two high frequencies, so it is almost flat except at the very beginning part. Here noise is present, which I told considered as a high frequency component. So in the high frequency region of the wavelet transform, we are going to have this noisy component. Now how to perform denoising? For this high frequency component, if you make it equal to 0, then most of the noise has got eliminated, right? So that's what the shrinkage rule. Shrinkage is not being applied to the low frequency region, it is applied only to the high frequency component region, because almost all the noise components lies in the high frequency region. That's the clustering of different frequencies. That's what is being happening over here. High frequency all together at one position, low frequencies at the another position. This is how the shrinkage is going to work for us. Okay, so with respect to transform domain denoising, we are going to make use of one method in a very simplified manner. It is being explained, the multi-spinning, and then an extension of that in a two different levels is being performed, just to identify how the research can be done in that way also. That is the multi-level denoising is being represented. Here we need to understand that has been previously told itself. Two different procedures are there. One is term by term denoising and one more is the neighborhood consideration. Anyway, we will discuss both of these two and their effects later in the results. Let us go through the concept of multi-spinning. So how this the basic concept of multi-spinning. So original image is there. We are going to create a replica of this original image by shifting the rows and columns. So this is with no shift. This image with only row shifting, this image with column shifting. So like this we are going to create several images, right? And that we are going to apply the procedure further. So how after shifting, how it is going to look like, that is being given over here. And our ideology is to get the edges at different angles. Now for the experimentation, our consideration is something like 7 images are being considered. They are circularly shifted, of which 1 image no shift, 3 image shifted row wise, and 3 image shifted column wise. Now the question is, why 7 images? Why not 10 images? Why not 20 images? Or why not something like 3 or 4 images? So this is a common criteria, because any number of images beyond 7 images is not going to give us any major results. Variation in the variation in terms of results, almost same result we are going to get. Therefore I just restricted for 7 images. If it is possible in some particular cases to get better results beyond 7 images, yes, one can adopt for the 10 images, 12 images, any number of images we can just consider for that. Now the procedure of implementation is given over here. Step by step you can clearly understand. Apply multi-spinning to nice image. Apply multi-spinning in the sense we have to perform the shifting of the images, row wise shifting, column wise shifting, and without shifting 1 image. Total 7 image we have to create. So that is what the concept we are going to have. Apply multi-spinning, then apply wavelet transform to each image. Yes, then denoise transformed images. Denoising, two methods you have to remember, term by term or considering the neighborhood. Both of these two has been verified. And then apply inverse transform to all the images, unshift and average them. All together, all these processes together can be represented by making use of this one formula, right? A simplified flowchart realization, same as I told in the previous slide, that has been represented in the flowchart. You can just, for very clear understanding. So start, then perform shifts, and then wavelet transform, denoise, then inverse transform, unshift and average. So that's what we discussed in the previous slide. Coming to the results, so here we can clearly understand noisy representation, Lena image 20. So the PSNR of this noisy image is 22.13. Several methods are being discussed over here. That's where we need to understand the concepts. Soft thresholding, and remember all these methods, soft, hard, translation, invariant. So these are all term by term thresholding, right? So soft thresholding, this is the result we have got. Clearly observable that we are going to have smoothing, over smoothing of the edges. So on the head the lines are not visible, and in this region it has got over smoothed. Then hard thresholding, edges are very much preserved, but on the other hand it is going to create the artifact, and also noise is still remaining. So by barrier shrinkage, so noise has been removed, but image has got certain effects that we can observe later. Then translation invariant, again soft thresholding is being used over here, and we can compare these two, soft thresholding as well as translation invariant. In terms of PSNR also it is better, and in terms of overall observation also the translation invariant method is better. Now coming to these three specific methods, so all okay, multispin soft, again term by term operation. So this is what we have got. When compared to direct soft thresholding, multispin soft is little bit better. This is nicing sure, noise has been eliminated to a larger extent, whereas some amount of smoothing effect is present. So multispin neighborhood method, in terms of PSNR it is higher, 31 point something, and also noise is eliminated to the better extent, and also the edges are preserved to a larger extent when compared to the nicing sure. For better understanding, a part of the Lena image has been taken, usually this line plus the constant gray level area for the comparison, and here we can observe the actual effect. Soft thresholding, over smoothing, hard thresholding, artifacts are created. So in the issues and the challenges we had gone through, artifacts are going to create, over smoothing of the edges is the issue. So these are the things that is required to be identified. Artifacts are created. Translation invariant better than soft thresholding. Bivariate shrinkage, yes, this is little bit better. Nicing sure, this is what the representation. Multispin soft and multispin neighborhood we are going to have, right? So for the better clarity, we have taken the error image and it has been projected over here. So as similar to the previous case that I have already explained, more clear representation over here indicates maximum amount of loss we have taken. So this is the soft thresholding, so we can clearly every structure is clearly visible, therefore maximum amount of loss has happened. So hard thresholding, we can observe so many dots we are going to have, almost close to this noisy representation, therefore artifacts are created and some amount of noise is still remaining. Translation invariant when compared to soft thresholding, so quite better. So bivariate shrinkage, so here and there still many of the data has been lost. Nicing sure, this is what the result. Multispin soft, again we are going to lose the information, and multispin neighborhood comparatively better to all of them, right? So again we have to remember the challenges, and the issues. Preserving the edges, creation of the artifacts, and also removal of the noise, all these three are the major parameters. So what we can observe over here, some shape, that is the edges. So we are losing the edges, that is over smoothing is happening at those criterias, where all we can observe just like soft thresholding, translation invariant, and plus multi soft. So these are the areas where we are losing the edges to the larger extent, so that's why these shapes are quite clearly visible. And where those shapes are not clearly visible, in those particular cases the amount of loss of the edges is quite less, not identifiable. Simply we can say it is not identifiable, therefore we say that is the better representation. Now let us get into the quantitative analysis. So PSNR is being used for quantitative analysis. So almost all the methods that has been represented in the previously, all of them has been taken for comparison. So Lena, Barbara, Boat, and the child images are taken. So noise level 10, 20, 30 and 40, and these are the results that were obtained, and in almost all the cases we can identify with respect to PSNR, multispin neighborhood is going to give us the best answers. uh, Mean structural similarity index, once again it is being taken and it is being applied on the in all these four cases, and here we can observe in most of the cases multi-spin neighborhood works better, and in some other cases nicing sure is also working better. Now the applying of this method on real images. So real images in the sense we don't know any information about that, we need to identify the noise. Same median absolute deviation is being used here also, and it is being applied on this real image, and this is what the result we have got. Anyhow, I have not elaborated this small section so that we can just realize it to the better extent. So just in the overall manner it has been represented. Now coming to one more methodology, that is multi-level image denoising. So what we discussed previously, so that method is one single method, so something like spatial domain. Spatial domain, one particular method we used and we implemented that. Transform domain method, wavelet, then one concept we just discussed on that individual. Now in this case, multi-level denoising, we are going to make use of two stages for denoising purpose. So in the stage 1 we are going to make use of noising sure. In the second stage we are going to apply the non-local means, and both of these two operations are being performed in the wavelet domain. Noising sure basically belongs to wavelet domain shrinkage technique itself, so that is wavelet domain. Non-local means is basically a spatial domain technique, and that is being applied in the wavelet domain. So any certain modifications are being done on these methods in order to avoid the over smoothing operation and also preservation of the edges. So certain small changes has been applied, not so directly we can just go through it. In this case, stationary wavelet transform is being used. So in the previous method it was discrete wavelet transfer. In this particular case it is stationary wavelet transform. So this is going to consume more amount of memory and plus it is going to hold more amount of information. So that's why the information is required for us. That means to be frank, getting best results is what is our importance. Therefore we are not taken care of the amount of memory it is going to consume. So that's why just for the sake of one verification we have just gone through this stationary wavelet transfer. So I'm just presenting this in a very simplified manner of a flowchart. You can just understand very clearly. Apply stationary wavelet, then apply noising sure, then apply non-local means to each of the subband, and then perform inverse wavelet transform. So we are going to get this denoised representation X cap. We are directly getting into the results. Only three representations. One is the noisy multi-spinning. Why multi-spinning means in the previous what we discussed, so this was the best in the PSNR, that's why that has been taken. And then proposed this is just now what we have discussed, multi-level, that has been taken as the proposed method. That's what usually the term used, so that's why I also used the same term. Okay, so now here we can clearly understand noisy image with noise is equal to 20 is present. 22.133 is the noise PSNR we are going to have. Now multi-spinning result already discussed, 31.188 we are going to have, and then proposed in the sense multi-level denoising 31.7598 we are going to have. Now make an observation with respect to the image. So noise is reduced in both of these two, that is a clearly visible criteria. With respect to clarity, if we go through, then this last method is going to give us a very high clarity of representation, so that you can observe on the shoulder region as well as this face region and forehead region. There you can clearly observe much softer realization has been done in case of this last method, and also we can identify that much of the edges are clearly retained. Therefore, so the methodologies are going to work. And one thing we have to clearly understand in all these things, image denoising is a well studied concept. If we take one method to the another method, to say our method is good, we cannot provide maximum variation. For example, in multi-spinning I have got 31.18, and for a next method I cannot say I have got 35 point something. No, it's not possible. So we can show only very small variation in terms of PSNR. That's what the maturity with respect to the denoising that has happened. And now the issue is how subjectively we can provide the best clarity of the representation. That is what the objective we are dealing with. And if the noise is too much, then how to restore that image. That is what the major aspects that is to be dealt with. Okay, so for a better understanding, the image part has been zoomed the face region, and here we can observe the noisy representation. Then after multi-spinning, here we can observe one thing, something like a washing effect has been observed here in some direction. So that has happened due to the rotation of the images. So here we can observe on the face region, we can observe all those things. So that is what the irregularity being created in terms of multi-spinning. In the last method that we have just discussed, no such washing effect, because multiple images are not being used over here. One single image with the stationary wavelet transfer, but two methods are being incorporated. And here also on the hat region, whatever the edges what we can observe over here, so most of the edges we are capable of retaining them. Even it may be something like this which is also present over here, and the lines what we can observe over here, that is also present over here. That's what the observable region, which we usually don't observe, but they are the observable regions actually. So and also on the face region, so clearly we can identify the differences between these two. The hair region uh, clear, much clear, face region much clear. So this is what is being expected, right? Now we'll move on to this PSNR realization. So it is always I must say this, in almost any kind of denoising technique you take, when the noise level is minimum, all the denoising techniques will always work to a better extent. Its actual picture comes when the noise keep increasing, right? So here also the same thing is happening. So noise is minimum, almost good answers we are going to get. As noise keep increasing, we can identify the variation. See 31, 31.7, so 29.2, 30.6. So variation between these two is changing. So here also same has happened, then both also we can observe. So structural similarity we are going to consider. So in almost all of them except this one, the last method, that is two levels of denoising, is going to provide the best results for us. Now image quality index, this is one simple criteria that we must go through. I have just taken one method, that is structural similarity. Is that the only one? No, that is not the only one available. There are several available, of which the most commonly used is the structural similarity index. So that's why everyone must get into this one. That's why I just introduced this structural similarity. There were several other defined, that is FSIM, GMSD, SSIM, we have already gone through that concept, UIQI. So these are the various image quality assessments we are going to have. Remember, quantitative analysis we say PSNR or the mean square error. That's the quantitative analysis we are going to say. And these four methods we call it as the qualitative analysis. Even though the value is quantitative, we call it as qualitative because they are not going to consider complete image at once and give us the solution. No, part by part it is going to take us, so that it can identify the errors in the local region. So that's why this is being represented as the quality assessment. Now, most important methods I must list somewhere. Almost we are at the end of the presentation. So important methods till now, most identified methods, the non-local means in terms of spatial domain. Non-local means then single value decomposition, BM3D, total variation minimization. So these are the spatial domain methods. In the transform domain, we are going to make use of the transforms like DCT, DWT, curvelets, counterlets, ridgelets, surelets, wedgelets, etc., etc. So there are so many transforms we can identify which can perform very much good way. So as I told you before contourlets, the importance of the contourlets, like that. Based on the application, identify what your application requires and then try to make any modifications in the existing transformation, or try to adopt one of the existing transformations so that it will work for for that one particular application in a better manner. Okay, so what next? So we have discussed so many things about image denoising. But is there any scope still now? Because as I told you before itself, in terms of result comparison PSNR, it can be clearly identified that there is not too much of variation in terms of the PSNR. A small variation after decimal point, 2 digits also. Okay, that matters a lot for us with respect to the betterness of the result. Then how we can still make it better? So what next? So that is what hybrid methods. What is this hybrid method? Combination of spatial and the transform one. For example, make use of total variation method along with the wavelet transform. So I have just discussed one method related to that. In the wavelet domain, that is the stationary wavelet I just presented. In that stationary wavelet, nicing sure is used and also non-local means is used. So two different methods in one domain. So that something like that I am saying wavelet plus total variation minimization method. One transform, one spatial domain. So hybrid methods are always going to give us the good results and also the better quality of the reconstruction. So graph cuts, so there are several papers from Vladimir, you can just go through that. Then boosting of image denoising algorithms, as far as the denoising methods are concerned, this is one of the good methods which is being papers are being published on this. So 2015 it is introduced. And then adaptive dual domain filtering, then adaptive boosting. So extension of this boosting filter, adaptive boosting, published in 2010. You can just go through this link for this paper. And then what challenge? So these are just generic. What we can say that we have taken just test images and we tried on that. Original images we tried on that. They are not specific to domain. So there's some medical image processing. No, we are not done anything with respect to discussed anything specific to those domains. And there are still challenges in such cases. For example, we can take medical images. In medical images, one image may consist of more than one noise. For example, speckle noise, Gaussian noise, both of them may exist in one image. So denoising such thing is quite difficult because one is additive, one is multiplicative. How to make a solution for that? So that restoration challenge is still there. And Poisson noise in the medical images, it is still there because in the medical images retaining the edges plays very important role, because for further segmentation process and all those things, those edges are most important aspects. So multiple noise in one image is what the major issue to be dealt in the medical image denoising. Similar way also satellite image plays a very different it will pose a very different type of noise because it involves the atmospheric noise and then the lighting conditions, and then one image cannot be taken all at once. It needs to be, it is going to take time for that. Then there will be certain other aspects that is going to involve, so that's going to pose a different type of problem. Then second thing, restoring in the presence of both blur as well as the noise. So that is need to be very much explored. If we try with the noise, then blur parameter is not going to work for us very well. If we just go with the blur, due to the noise, blur may hamper. Deblurring may hamper. So this is what the interesting areas that are still need to be explored. And with respect to only denoising, so medical, satellite, so these are the most important aspects that we need to concentrate on. And also identifying the fast transforms or fast denoising methods is important. Reduce the number of computation, give the better results. So accept a better or acceptable result. That's what the important issue, because nowadays the images are being used for several purposes, something like the real time capturing, as well as the independent vehicle navigation, vehicle purposes, vehicle driving purposes. So these things involves the real time identification, unmanned aerial vehicles. So real time processing is required, which is not supposed to take much of the time for us. So identifiable manner, clear image, it must provide us. So these are still remained as the challenging issues in image denoising. Okay, so finally I'm getting into the conclusion. So image denoising is a well studied problem in the field of image processing. I told you earlier that. So denoising can be achieved in spatial or transformed domain. Well, achieving great difference in the quantitative analysis, very important. Quantitative analysis is very hard, but some of the methods can establish good mathematical view, that also I told about you. Mathematical view that can be applied for various kinds of images like medical, satellite, CC camera, etc. More methods are being expected that can achieve better quality outputs. So that's what is required further as a further research. Okay, so this is the end of my presentation. Before saying thank you, I must acknowledge. So I acknowledge Dr. K.V. Suresh sir, Professor SIT Tumkur, for his guidance in the field of image denoising, and also my sincere thanks to the organizing committee of Vidyavardhaka College of Engineering, Mysuru, for inviting me to present this session on image denoising. So thanks for your patience listening. Thank you one and all.